Have you ever wondered about hydrocarbons? No? Well, maybe the oil in your kitchen, the fire on your stove, the petrol in your car, the plastic in your bottles, or maybe even the polyester sweater you're wearing. Ever wondered about any of those? Still no? Wow, you've got no imagination, but don't you worry, because I'm going to tell you anyways. Welcome to the thrilling tales of Harry the Hydrocarbon. Now you see, a long, long time ago, there was a merry little bacteria swimming happily under the sea. But as with all living things, it died. Yes, very unfortunate, I know. It has only been 12 hours or so after all. But anyways, the corpse of this little being, Barry, was swept along the ocean waves, and eventually it sunk down and down below into the ocean floor. And there it stayed. The sands and rocks piled on top of it, they buried and crushed the little bacteria buried deep, deep underground. Now, as you can imagine, being buried is not fun. You're subjected to intense pressure from the rocks and the sands and the heaps of water upon water and unimaginable temperatures too. So you can probably guess that Barry the bacteria was bacteria no more, reduced to its fundamental building blocks, carbon and hydrogen, hence the name hydrocarbon. This keeps going on for a while, more pressure, more rocks, more heat for billions and billions of years, and boom, you get the carcass soup that is oil. That is, until humans get their hands on it. Then that soup will turn into liquid gold. I'm not going to, nor do I have the time to, bore you with the details of how this does get extracted and whatever. Long story short, you drill a long tiny hole into the ground into a pocket of oil, and the oil, because of all the pressure underground, is forced out into the long metal straw thing that you just drilled, an oil rig, and boom, you get oil. It does get more complicated than that when eventually there is not enough oil or pressure to force it out, but this has already taken up a paragraph of script, so go Google it or something. Fast forward, we get crude oil, where Harry the hydrocarbon is drifting around. Now, within hydrocarbons, there are different types of homologous series, like alkenes and alkanes, for example. Within each series, they follow a set of patterns for the molecular structure, or a general formula, and they have similar chemical properties, and their physical properties follow a pattern up the series. Alkanes, the boring, saturated, single bonds bunch, have the general formula of CnH2n plus 2, while alkenes, the fun and exciting, unsaturated, reactive, and double bonds bunch, have the general formula CnH2n. Going up, they follow a naming pattern. There's methane, ethane, propane, butane, pentane, and ethene, propene, butene, and pentene for 1, 2, 3, 4, 5 carbons, respectively. But you see, because of their different physical qualities, you can't just use crude oil on its own. When you try to use it as car fuel, only half of it will combust, if that, and it would also be horribly inefficient, because you would be using smaller molecules with less energy to have limited utility on the car itself, when instead they could be used to, light a fire, cook lunch, be the magic healing gel on your cuts and whatnot. So we have to separate them. But how do we do that? A fractioning column! What's that? A giant tube! Yeah, it's basically a giant tube, but really a chimney on the commercial scale with different levels in it. Firstly, the crude oil is heated to about 350, 400 degrees Celsius, and even then some of it will remain liquid. These, called bitumen, will stay stuck at the bottom of the column, because liquids are unfortunately victims of physics. Gas, however, are not, and so the vast majority of the oil will rise up the ranks and climb the ladder. As you get higher, the temperature drops, and there's trays in between stages to catch any condensed liquids. Since the temperature drops, the hydrocarbons with a longer chain, as they tend to have a higher boiling point that was boiled in the first stage, might too succumb and become liquid. These that pass the first test but not the second are called fuel oil. Yeah, it's a boring name. The process repeats, going up the tube in order of boiling point from highest to lowest. We have bitumen, used for roads, roofing, and sometimes paint. Fuel oil, used as, you guessed it, fuel for ships, factories, and central heating units. Diesel, used as fuel in trucks and vans. Kerosene, fuel for planes, jets, lights, and cooking fuel, sometimes fuel for rockets. Naphtha, used as a solvent in cracking, which will be explained later. Soaps and cleaning fluids. Petrol, fuel for your car and your small talk and your political debates. And finally, refinery gas, for heating, cooking, and all that stuff. This, my friends, is liquid gold. It is in everything from your stovetops to your clothes to your car to the plane you drove for vacation to the heating in your house and probably even the electricity in it. It is better than liquid gold. But surely something so good must have drawbacks, right? I hear your cynical brain thinking. And you'd be right. Of course you'd be right. What exactly happens when we burn and thus use this stuff then? Well, there's 3 major concerns: nitrous oxide, sulfur dioxide, and carbon monoxides. The former 2 as a result of sulfur or nitrogen impurities in the oil, and the latter as a result of incomplete combustion due to a lack of enough oxygen. They hence have quite different dangers to them as well. Nitrous and sulfur oxides, formed as a result of the impurities, harm us in a more roundabout way. They rise in the air once released and mix with the water in the clouds to form sulfuric and nitric acid, which then gets rained back on the earth. If that doesn't sound exactly swell, it's because it isn't. The acid seeps into the ground and dissolves nutrients in the ground, preventing trees from being able to take them up. It can alter the pH of bodies of water, thus harming marine animals and plants, and it just makes everything acidic, which just kills everything, which is arguably not good. Carbon monoxide is more direct, though. These could bond with the hemoglobin in your blood and thus reducing the red blood cells' ability to transport oxygen, thus lowering your rate of respiration, which is bad. The most painful part of CO poisoning is that you don't even know. Breathing it in could kill you in minutes, and you'd suffocate while breathing, and you won't be aware of it. This is especially prevalent in car engines, as they are in an enclosed area and thus do not have enough oxygen to complete combustion. Oh, and there's particulate matters, which is the thing that causes all those air quality warnings. So yeah, generally uncool. It kind of sucks. Do you want to talk about isomers instead? Yeah, that's what I thought. Isomers! You know that thing called isotopes where the same elements have different neutron numbers? This is like that, where they have the same number of elements, hence the same molecular formula. What's a molecular formula? Let's talk about that. So essentially, there's 3 ways to write chemical molecule stuff. There's the molecular formula, the structural formula, and the displayed formula, where you draw out all the bonds and stuff. Yeah, anyways, back on track. Same molecular formula, but different display formula. So this is butane. But this is also butane. Well, not really. It's isobutane. It's also methyl propane. Methyl because there's 1, and me is the prefix for 1, and propane because there's 3 left on the branch, and prop is the prefix for 3. Isomers like methyl propane tend to have a lower boiling point than their straight chain counterparts, as straight chains have more points of contact, hence a stronger intermolecular bond, thus harder to break, while branch chains have lesser points of contact, weaker intermolecular bonds, and thus easier to break. Remember the fractioning column? Yeah, hard transition, I know, but remember? Well, did you know that the longer chain hydrocarbons are actually kind of useless? Yeah, we have, way higher demand than supply for the shorter ones, too. So, what to do? If only there was a way to turn long hydrocarbons into short hydrocarbons. Oh, wait, there is, and it's called cracking. In short, cracking is where a long hydrocarbon, usually alkanes, are broken down into shorter alkenes and alkanes. This is especially useful because we can use the alkenes for plastic production later. This could be done in 2 ways, thermal and catalyst. Thermal is where the alkane is basically put through torture, temps of 600 to 700 degrees Celsius and pressures of 70 atm, until it, cracks. Catalytic needs lower temperatures and pressures, but as the name suggests, requires a catalyst, something silica aluminum based. Here's an example equation where octane is cracked into ethene and hexane. In a lab, you can do catalytic cracking with the following setup. Mineral wool soaked in oil placed at the end of a tube, the catalyst, aluminum oxide, and a bung with a delivery tube into another tube submerged under water. Then you heat the tube, mostly the catalyst, but heat the oil every now and then for a brief period of time too. And there you have it, that sweet, sweet equilibrium point where the 2 lines meet. That supply and demand graph of all the fractions. The graphs that you might want to draw on whiteboards. The whiteboards that are made of, you guessed it, crude oil. But wait, this and this are kind of not the same thing. I mean, never judge a book by its cover, but I mean, that's liquid and that's distinctively not liquid. Well, that's because, children, it has to undergo polymerization first. Why are we still not finished? Polymerization! What on earth is that? You know how alkenes are reactive, right? That's because they have a double carbon bond, which means that the bond could be broken and joined with something else, like chlorine, bromine, and whatnot. But what if it joined with more of itself? That's what polymerization is, really. You can make polyethene, polypropene, polybutene, all that, by just joining the monomer, ethene, propene, butene, with more of itself to make polymers. And these polymers are what makes plastic. For example, polyethene is what your cling wraps are made out of. Polyester is what makes up styrofoam. And there's even Teflon, which is technically not a hydrocarbon, which makes up your nonstick pans and humanity's doomed itself arguments. Speaking of which, have we actually doomed ourselves? Plastic is an amazing invention, and it has changed the world in thousands, if not millions, of different ways, but when you open your phone to read the news, or really scroll social media, all you see is people complaining about how plastic is evil, and we're all gonna die. Mass hysteria, am I right? Well, is it hysteria, or are we actually going to die? I am not qualified to answer that question. I am a random person with no qualifications who's connected to the internet. I am not credible. What I can answer, not so much can as have to, is what is on spec. The different ways one can dispose of plastic. On one hand, we have the all-or-nothing risk-taker burning. Burning plastics could actually be an energy source, and the energy harness could be used to do what energy does, like power homes, generate electricity, and whatnot. However, burning plastics, which at its core is a hydrocarbon, leads to the typical burning hydrocarbon problems, such as greenhouse gas emissions and hence pollution. On the other hand, we had the safe and boring approach. Landfills, the all-time classic. Out of sight, out of mind. These don't release greenhouse gases as plastic is not biodegradable, and they don't release toxins into the air. It does, however, pollute nearby waterways and serve as a breeding ground for bacteria. It is also just ugly in general and takes up a lot of space. That is the longest script I've ever done. Oh wait, this is supposed to be about Harry. I did not forget about that. Nope. Harry. Oh, Harry. Harry, you're a wizard. Actually, go on, I know you must be surprised. I was too, when I found out, but I believe in you and your burning ambition. Oh, but don't get too ambitious, though, else you might be stuck as reflux forever in the Hogwarts fractioning column trademark. Thank you for watching. Bye! Do you know the thing called isotopes, where there's the same element that have different proton numbers? I can't believe I wrote that. I cannot believe I wrote that. Oh my god. Okay. Okay, I see how that is.